So, let's begin. Good day, and thank you for joining SKF's SimPro Quick webinar. My name is Wesley Alexander, and I'm an applications engineer for SKF. I work in various industrial segments such as food and beverage, pulp and paper, metals, and agriculture. I have found SimPro Quick to be a very useful tool in all of these industries to accurately model an application to obtain specific results. So let's take a look at a basic overview of the software and its capabilities. In SimPro Quick, you can model a single flexible shaft. You can have access to a full range of SKF bearings. You can model multiple bearings on a single shaft. You can model the effects of the influence of fits and temperature and how it affects operating bearing clearances. You can model multiple gear types. You can add a spring for preload. You can add spaces, and you can add or import a 2D file such as a CAD drawn shaft, for example. That way you would not have to redraw that in SimPro Quick. Some other capabilities of SimPro Quick: it allows you to calculate bearing loads, bearing load zones, contact stresses, bearing friction, bearing frequencies, shaft deflection, bearing life, and the list really does go on for quite a long time. You can get very good results using SimPro Quick. On to the next screen. This is really the main screen of SimPro Quick. It's called the modeling desk. This is where you build your model and define all your parameters. So for example, what we see on the screen is a section of a bearing shaft with two bearings on it. What you can see are the operating conditions for the application. So for the main operating conditions required really are speed, loads, lubrication, gravity. I will explain why when we get to that point, and fits and clearances that can be defined as sort of the last step in the process. Without further ado, let's take a look at today's example. So today's example, we will be looking at a fan application. The customer has kindly allowed us to use pictures from his site in this presentation because it does not really reveal anything about the site or the customer. What you can see on the screen are 4 industrial fans, a motor, and a shaft system. On the other side of the chute is a impeller. So we have a motor driving a shaft system with an overhanging impeller, and the whole process is to remove heat from the operating process. Okay. The reason why we want to run this calculation today is to verify the performance of the bearing arrangement regarding the bearing fatigue life, regarding bearing loads, the misalignment, and to evaluate the shaft deflection under the current loading conditions. Also, most importantly, we want to ascertain if using a roller bearing over ball bearings will be sufficient in terms of meeting the minimum load. So this is a self-aligning system, and we want to ensure that the minimum load on the roller bearing is met. If the minimum load is not met, this bearing could suffer from premature failure, for example, just one of the things. On the right hand side, you can see the operating conditions that we will be putting into the application. So speed, the motor size, which is 7.5 kilowatts, pulley diameter, the motor torque, the weight of the impeller. So if we imagine the impeller will be sitting here, a thrust force of 150 Newton in that direction, and a belt angle of 60 degrees. So that's the belt angle there, 60 degrees. The distance between the two axes is a meter. So without further ado, let's go into SimPro quick and start playing with the software. I would encourage you at this point to take a screenshot of this. I will do the same at this point, just so that we have a copy of the shaft that we are trying to build. So I will take my screenshot. Feel free to take your screenshots now as well. Drag it over to a different screen if you have two screens, or just keep it in the background in case you want to refer to it while we are watching the video, while you are watching the video. And I will then move on to the software. Okay, so this is the main desk in SimPro Quick. SimPro Quick follows a logical application simulation process, in which the entire simulation process is split into 4 stages. Stage 1 is the modeling desk. This is where the model is built and operating conditions are defined. Stage 2 is the analysis variations desk. This is where the model analysis is defined, whether it's a static analysis, load cycle, or axial pre-displacement analysis. The report desk, which I will not click on right now, is where you can see the results of the model. And the graphical results desk is the 4th and final desk. And here is where you can view a 3D animation of the model, as well as looking at a graphical representation of some of the items in the report. Okay, let's move on to the model and let's build our model. Before we start that, I will quickly explain what some of these icons mean over here. So SimPro Quick follows a stepwise, or it has a stepwise graphical interface, which follows steps to build your model. The steps are sort of in order. So should you just follow the order here, which is defining your shaft, adding a housing, adding your bearings, any gears that you might want to add, any springs or spacers next. Once those are defined, you can start looking at adding your rotational speed, forces, pulley forces, gravity, lubrication, fits and clearances. So let's follow those steps as we build our model. First, let's define our shaft in the easiest way. I like to click on the shaft that you're given and start editing its length. So the length of the shaft that we're working with is 800 millimeters. The size of the shaft is 60 millimeters in terms of diameter. The shaft is split into about 5 sections. So we will be very close to the screenshot we've taken, but to save time, it will not be precise. If you go to the top of the screen, you can enable or disable section split mode. So let's enable section split mode and split the shaft into 2 sections. Disable it again. You can access that section split mode simply by holding down Control and pressing Shift. You'll watch the mouse and see how it changes. It then changes, and you can continue sectioning the shaft. Okay, the shaft is now sectioned. Let's change the diameters of our sections. Let's call this 65 millimeters. Let's call the next section 70 millimeters. Let's call that section over there 65 again. And the final section we can leave it at 60. To change the length of the different sections, you can simply drag and drop. You can simply drag it along the x-axis, or you can simply type it in. I will type it in. Let's call the first section 240 mils. Let's drag the next section to about 60. Let's call the next section 200. The next section is not really that important. Let's put it at about 65 again. And that's the final section, and that's what's left of it. On to the next phase. The next step is to add a housing. Once you have completed this step, by the way, it goes green. Let's add a single housing to show you what it looks like. Once you drag a single housing onto your shaft, it appears over the whole shaft. So for example, we will not be modeling today a twin bearing housing, but this could represent a twin bearing housing, or it could represent a roller that rotates. So let's remove that because we will not use that today, and we have to be mindful of time as well. Dragging on our first bearing, we will drag it onto the 60mm section of the shaft. Notice that when we drag the bearing on, a window pops up. This window pops up in order for us to choose what bearing we want. It also already sets some limits in for us to search for. So it set the shaft size. So it will only be searching for bearings of 60mm in bore diameter at the moment. We can also click on popular items only. This will only bring up the bearings regularly manufactured and popular with customers. So what we want to do on the left hand side of the shaft is have a carb toroidal bearing. Let's search for that bearing. Okay, that's the bearing we want to use. Now before we click on to use it, what you can do in the top window, instead of having the bearing called SKF bearing 1 in your report, you can use designation as name. So we enable that. The moment we click on the bearing, the name changes. So in your report, you will have that as your bearing name. Okay, we've added the bearing. It is now asking us to constrain the inner and outer rings. We are using a carb bearing in this case, so both rings will be fixed. To position your bearing, you can either drag and slide it along the shaft, or you can align it to the left using the icons above. You can align it to the right, or you can put it into the center of that shaft. In this case, we will just align it to the right of the shaft. The next bearing we want to add to the shaft is a self-aligning ball bearing. So now that we've dragged the bearing onto the shaft, similar process. We only really want to search for popular items, and we want to look for self-aligning ball bearings. So let's do the search. The most popular self-aligning ball bearings that pop up are below, and we want to use that one, a 121 ETN9. 1212 ETN9. Let's add that bearing by double clicking on it. The bearing is now added, and what you can see is the same window asking us which rings are fixed, which rings are actually free. If, for example, we were not using a carb bearing, we would need to have at least one bearing axially free in order for that bearing to rotate, to slide in the housing. Let me show you the difference. So when your bearing is axially free, it will be able to slide inside your housing. But because we're using a carb bearing, that sliding takes place internally. And the sliding is necessary to be able to accommodate thermal expansion. So in other words, that's the free bearing, and this is the fixed bearing. Let's make that fixed. You can now align that bearing to the position. Let's align it to the right of the shaft. Now, if we had any gears to model, we could drag and drop that onto the shaft. We'll have a different selection of gears to add, if it was, for example, a spur gear. That's what it would look like. However, in order to get it looking correctly, you will need to choose the correct bore diameter and define all the parameters of the gear. Let's cancel that. If we wanted to add a spring, we could just drag and drop that to the inner or outer rings, and it will apply a spring load. You can then after that define the magnitude of the load of the spring. Any spaces, you can do that next. Let's move on to the operating conditions. So the first one we have is rotational speed. Click on that and change the speed to 1460 RPM. Drag and drop the load to the position that you want your loads. In this case, the load is on this side of the shaft, and it is acting in a down direction in the y-axis, and it's 500 newtons in magnitude. Position your load accurately. Next, we are going to be adding a pulley force. So there's a belt pulley on the right hand side, if you can remember the drawing. If you didn't take a screenshot, that's the drawing. We want to remember that we have about a 60-degree angle of the belt pulley, and the rest of the information is here. So let's go ahead and put that into the application. So we're dealing with kilowatts. The applied power of the motor is 7.5 kilowatts. The design torque is 20 Newton meters. The pulley diameter is 158 meters. And the other pulley diameter is also 158 meters, since it's a 1-to-1 system. The distance between the axes is 1 meter. And the angle, let's call it the belt angle or azimuth angle, is 60 degrees. The pretension factor, if you're unsure what any of these are, simply hover your mouse over it. It will then give you a definition of what it's asking for. So the pretension factor in this case for V belts is 2.5, which is what we will use. Okay? Next, we have gravity. Let's enable gravity. Simply what that means is when you have gravity acting in a down direction, you're basically telling SimPro Quick that your shaft is in a horizontal position. If you add gravity acting leftwards or gravity acting rightwards, you're telling the SimPro Quick that your shaft is vertical and telling it in which direction in the vertical axis your shaft is operating in. Our shaft is horizontal, so it's acting in the downwards direction. Next, onto lubrication. You can select from a suite of predefined SKF greases. I will choose in this case LGW82. LGW82 is a wide temperature grease suitable for a wide range of applications and used by several fan manufacturers. So we've chosen that and applied it to the bearings. If you wanted to create your own grease, you could do that. You could click on create new, choose a name for your grease, click on OK, and start defining the parameters of the grease. So your viscosity at 40, your viscosity at 100. If your oil was different to the standard mineral oil, you could then change that in that section. You could change all these parameters. Let's cancel. Let's click on OK. So our grease is now, our lubrication has been added to the model. If you look at the bottom, as we've moved along, so has the icons at the bottom. If you wanted to go in and change your shaft, for example, you wanted to have a hollow shaft, you could do that. Instead of being a cylinder, you could make it a tapered cone shape. You could change the material of the shaft. So you could select from a predefined list of materials or you could create your own material again. Add your own material, and you can define the Poisson's ratio, Young's modulus, the density, and everything else to do with your new material. Okay, let's move on to the final step, which is your fits and clearances. So click on fits and clearances. What you'll notice is at the bottom it brings up the fits and clearances tab. At this point we can change the shaft tolerance, so from K6 to something else, but we are only really interested in the housing tolerance, since these housings will be able to use a different tolerance in the actual application. We are choosing a J7 instead of the standard H7 housing tolerance. Right, once we click on clearance reduction, it does some calculations and it calculates the estimated operating clearance in radially and axially based on temperature, speed, and your fits. Now, if we change the temperature of the inner ring to about 90 degrees, watch how the operating clearance of the bearing changes. So it drops quite a bit. So the operating clearance for the 1212 is not actually very good, because it's in the minus, which means the bearing is in preload. So that sort of temperature difference between the inner and the outer ring is major. Let's leave it like that and go into the report and see what effect that extra preload is adding to the bearings. Right. Next step is to decide if we're going to be doing a static analysis or load cycle analysis. In this case, it's a static analysis. In the report section, it's asking us, do we want to save before going into that? I will this time say yes. I'll save a test and we'll move forward. Once you click on report, it starts doing all the calculations. If you go into your model and come back to the report, it will recalculate. But you can always update for the latest calculations if you're unsure. In the report tab, you now can see the full results of your model. You can also on the front page see a 3D model of your actual application. And finally, we can start looking at the results. Now, let's start with the bearing life. So your bearing life for both bearings, in fact, is looking very good, despite the preload on the one bearing. Bearing life is above 100,000 hours in every case. So your basic bearing life is your L10 bearing life. Your SKF load-based bearing life is based also on takes into consideration lubrication and temperature, as well as contamination. Bear in mind that it's worth mentioning at this point that bearing life is only really reliable for a kappa ratio between 0.1 and 4. Anything outside of that, really, the results cannot be relied on. Well, it's not perfectly accurate for that anyway. Next, we really want to have a look at some of the checks. Let's go into some of the checks. So SimPro does all these checks for you. It doesn't give you the results of the checks, but it allows you to be satisfied that your static safety factor has been checked and all the rules pass. Your permissible misalignment is not more than the allowed, so that passes. Your minimum load checks out pretty well, so there is no minimum load issue. In other words, using the roller bearing over the ball bearing is not a bad thing. It's not it did not fail the test. Your life model validity, so it's between 4 and 0.1, which is what we just discussed. And yeah, all the checks check out, so nothing wrong yet. What do we see at the moment on the next screen? This is all the input data. These are the bearings we've chosen and all its data. Next is lubrication data that we've chosen, LGAW2, and the temperatures, 90 degrees for the inner rings and 70 degrees for the outer rings, which is not going to be accurate in terms of what's actually happening in real life. On to the next screen. Onto the results page. So on the left hand side, you have sort of a table of contents that you can go through. You can delete things that you're not interested in seeing in the report. You can add different tables that are not in the report. You can add more to your report if you wanted to. Right, in the results section, we have bearing loads, static safety factor, and C/P that you can see over there. These are the calculated bearing loads for each bearing. Over there you can see the C/P, bearing contact data, bearing clearance, relubrication interval for grease. So every 5,800 hours, the bearings require 12.1 grams of grease for the self-aligning, and for the car bearing 15.4 grams of grease every 2,800 hours. So not very much grease. If you look at the previous example, remember the customer is experiencing bearing failures with this arrangement. If you look very closely, you can see a lot of grease being purged in these bearings, which means these bearings are virtually over-greased and are overheating as a result of it. But customer is greasing the bearings extra because they're making a noise. But really, they're using the wrong bearings for the application. And that's the reason for the noise. That's not actually the reason for the noise. The reason for the noise is there is an imbalance on the impeller, creating vibration in the bearing. And that vibration is removed when you use... it's not really removed, but it is... it is not really acting on the bearings. The vibration is still there, but the bearings, it's not really affecting the bearings, let's say it in that way. Next. Lubrication conditions. We can have a look at bearing life. We can have a look at bearing friction and power loss. So there your power loss, 9 watts, 27 watts for the carb. Bearing frequencies. Bearing shaft displacement. It's better to view this in a graphical representation, which we will do in a few minutes. And all this information in the report. Okay. That's the report for you. In other words, we've successfully modeled the application. We've checked the minimum load. We are happy now to go ahead and use this bearing setup or propose this bearing setup to the customer with a reasonable degree of confidence and a reliable engineering calculation to back it up. This is an accurate representation of the shaft. This is a very accurate animation. So this is actually, no, I'm just kidding. This is an exaggerated animation, and it's just really showing you which direction the loads are acting in. So the pulley is pulling the shaft up, the weight of the impeller is pulling the shaft down, and you're getting a good amount of load acting for this bearing to operate in its optimal conditions. Moving on in the graphical in the graphics results, shaft deflection. So that's what your shaft is doing in the while operating. As you can see, there's a very little amount of deflection, 60 microns. Shaft stress. So we have bending moments, bending stress, shear force calculations, all done for you. Bear in mind that this is not an FEA software, so it's very basic calculations that are done here, not FEA. Bearing contact load. So these are the loads on the inner ring. Each one of these dots represent a roller position, and at which position, call it 270 degrees in this direction, so downwards, you have rolling element number, I don't know, 7, 8, 9, and 10 in the load zone with quite a substantial radial load. Well, enough radial load. Bearing contact deformation, similar idea. Bearing contact angle and axial predisplacement, which we do not have. So that's the complete model. I hope it was helpful. I hope it was useful, and I hope that you all feel more confident now to be able to use the software. Remember, you can always go to the icons above, the options, and scroll down to report. You can change your user name, so every time you produce a report, all this information will already be in. The only conditions you will need to add are the customer's details. In the report section, you can change the language as well. So these are the available languages which the report can be published in. Doesn't always need to be in English. Finally, to download SimPro Quick, you simply go to your web page, type in skf.com. From the skf.com web page, you can go to support, go to engineering tools, click on it, scroll down. If you do not see it on the front page, filter the product platform by bearings and units, and SimPro Quick will come up. Click on SimPro Quick and apply for the software. So scroll down, apply for the software by registering. Once you've registered, you will be granted a 90-day free trial of the software. After 90 days, if you've used the software and you're happy with it and you would like to have it permanently, simply contact SKF. Thank you very much for your time today. Enjoy your day further. Bye.